Now the first example is just like a Schrodinger equation. Um, they start with the Schrodinger equation and take the Fourier transform, and basically you divide an equation that involves the Fourier transform of the wave function. Uh, Another way to look at that is that wave function, the Fourier transform of wave function becomes you can say a wave function in what we call the momentum representation. You, you learn about different representation. Like not all of you have taken quantum. Right? I'm sorry, some of you taken quantum. Right? So, we talk about that different representation. So usual wave function in the Schrodinger equation, we call it the spatial representation. Basically, it's using the spatial eigenfunction as expansion, and the wave function is the coefficient in front of the spatial eigenfunction. That that is what a wave function. But if you don't like that, you don't want to look at this in a space of the eigenfunction of momentum eigenfunction, that becomes a in the momentum operator. And this example is just to show that equation in momentum representation is just taking the Fourier transform. It's just the same. So you start with the Schrodinger equation in one particle and one dimension. Obviously, you can generalize that to three dimensions. Doesn't, it's straightforward. Wave function psi as a function x is v potential evaluate x to psi. So consider eigenvalue E of the energy eigenvalue. Right? That's the Schrodinger equation with time independence within Schrodinger equation. So now you just take the Fourier transform, and then your textbook using the t function, but it doesn't matter. You can whatever rotation you want to use. Like consider this the Fourier transform of psi as this becomes in case. I think later on the textbook using G first, and then some other change of variable later. But this is the Fourier transform of the wave function psi. We call it, just give it a name G. Now I take the Fourier transform of both the left hand side and right hand side and term by term. But this term is okay, so you know how to do the derivative, right? Yeah, b squared b x squared psi. You know how to do this one. One of the property I asked you to do in the homework. Right? Remember that? What is this? What is this? No, remember. Just two derivative of the psi and take the derivative. What is that? You multiply by a factor of t. What is the factor in front of t? Yeah. Yeah. That should be. I mean, I derived that in three-dimensional space, but the homework asks you to repeat all that in one dimension. It's just one variable for each transform. And the way to do it is the same. Just uh, do what you call integration by part. This is 2 times with integration by part minus k squared. Okay, so this term you can take care of. So this term is straightforward. And now the potential term that you applied. So you can either use the convolution or this the last formula that we used. Now becomes we use that with what we just derived as 1 into k. And we evaluate at 1 into k and operate on t. Okay, so change all the x in the potential function to operate the ddk. Right, then obviously then you can write down the equation in Fourier transform. So just change everything. There's a minus sign, right? I don't copy. So minus sign and the minus sign. This becomes k squared over 2m and g and then plus e dd g equals to this e. Right, that is like that is, I mean, a valid equation. This is equivalent to the original Schrodinger equation, but in order in the Fourier space. Basically, G is the Fourier transform of the wave function, and then you can put in a standard form of the quantum mechanics. I think the textbook doesn't involve the h bar. That should be h bar here, right? H bar square, h bar square. Right? And but anyway, if you do the usual notation, I think the momentum is in the textbook. Yeah, momentum I think is defined as minus I d here, right? And so that's original is the momentum, and so that this one is just basically this using that you can change the v as a function of this become v as a function of p. Right? No, I'm sorry. This is still ddk. This is ddk. I think that this is going to here. This is originally is p squared, right? If you in the momentum in the original physical space, that p is in terms of ddx, right? But this operator is ddk. Actually, change it back to x. This is becomes x. So you can say x is minus I. Yeah. G is k. G is this. We are doing Fourier transform up to here, and then but we want to identify some. Yeah, up to here you can forget about momentum first because this is you write down the Schrodinger equation like that. This is a differential equation x. They do the Fourier transform up to here still Fourier transform. Just doing Fourier transform x, and then all these function depends on k. But now we identify that I should say uh, because we this is like minus p squared. So this is if you now define your momentum like that, define your momentum as operator, which is going into here. So this becomes p squared minus p squared. So right, because p is operator like that. You put it into here. That is minus p squared, right? And then after you transform, so after you transform, you get a minus k squared. So you can identify p as k also. So whatever your Fourier transform variable, that wave number actually now becomes momentum. And although your textbook ignore all the h bars, that you restore h bar as h bar times k is your momentum. So now you can use that to rewrite this equation, and I mean in the general, I mean in the definition of momentum, this becomes p squared T n times g. Now it's everything changes to depends on momentum, and then plus v that is 1 over I v dp, because p is the momentum, p is just k. G, what do you call G? Yeah, you can call it the wave function in momentum. Or in our case, G is just the Fourier transform of the wave function. And it turns out it be exactly the same. I think your text will also involve taking the complex conjugate, but that's a matter. Whether you take the complex conjugate and not complex conjugate doesn't really matter. Okay, because the wave function you later on you set the coefficient, and you want to calculate probability and all that, both the wave function and its complex conjugate anyways, because just the probability to find a particle is proportional to psi absolute value squared. So you involve psi and its complex conjugate. So where they talk about complex conjugate, not the same. Yeah.
Yes. So my question is about so we just identified the rest just operator, like the way you have done for the top part of the potential.
Yeah.
That we have x. So we just say that the x part is the one that can be the y, the x one, that one is the dx. Now we have using the like the guiding is just take it beside like even using this or someone before something before and then you use the
Sorry, I kind of follow you.
What I'm asking, the previous example, I think I was asking
the previous example, which is just the product of the two functions, right? Yeah, basically this Fourier transform of this product is given by a previous discussion as v, and then substitute this operator in x, right? Whatever the v as a function x is, just substitute this operator in x. So the whole thing becomes operated. They operate on G, which is the Fourier transform of psi. Is that okay? Is it clear? All right. So whatever. So this becomes another differential equation instead of the original differential equation, which is second order. This can be arbitrary order because if you have an arbitrary Taylor expansion, this is infinite order, and it doesn't make any sense actually, right? But it may not be easy to solve anyway. So therefore, you probably never see something like that in your quantum mechanics class. So you usually just solve in the physical space, right? Yeah, yeah. Yeah, this is P is like that, right? Yeah. This is negative p squared, but after you do the Fourier transform, actually get a minus k squared. But this is for the case. But in the Fourier transform, you transform only psi, not p. The p taken care of, so you identify p equals to k. Yeah.
So that negative and that negative cancel. So it's k squared.
Okay. So, all right. So that's just one example to write it down this form, but it might not be useful. The next example is slightly more useful, but we're going back to the convolution actually. Convolution of instead of writing it as operator equation, you go back to the convolution. So this is, I mean, it's slightly more useful, but the equation in the fluid space also not easy to solve. Now this is a 3D, 3-dimension. This is the next example, 20.4.4. So now the text will actually ignore the M. It doesn't matter. Three-dimension, so the path here, and the potential is specified as your Coulomb potential 1/r, and ignore okay, ignore all the coefficient like 4 pi epsilon 0, all that. Solve this. Okay, now you do the same procedure. Take the Fourier transform of both sides, and again this becomes just k squared. This is k squared over 2. And your variable is little phi. Okay, in the textbook. Now, the left hand side is easy. It's just so, right. It's the middle part that we will need to work on. And now instead of using the operator, you go back to the convolution part. So take the convolution between the Fourier transform of 1/r and Fourier transform of psi, which is phi. Okay, you can write the formula. So using that definition, and I think you're 15 phi psi k, and then the 1/r Fourier transform. This is 3D Fourier transform, and then you add it. And this is dqk. Right. Writing as a convolution. The convolution is just integrating over function, right? So you have two functions. This is the Fourier transform of the psi and phi, right? This is, we write it down right away. This 1/r is also a Fourier transform, but you evaluate x minus x pi, k minus k pi, and the integrate over k pi. So the integral will involve only k. After doing the integration, it's just a function of k. So, right. So this is not an operator. This is just an integration. Well, product of function, right? And that's what we define as a convolution. It's still a function. A convolution is still a function. Okay. But what the previous example is, whatever this operator, you take the Taylor expansion and we divide everything, and this is not an operator. After you take the Fourier transform, this is just a number k squared. Okay, this is just product between k squared and the wave function. I mean the Fourier transform with the wave function. And this becomes just the only operation in this equation is the integration. Okay, but that's no it's different formula. The previous example is just the v value at that differential operator. That we're not applying that to here. We are applying. This is just the convolution between the Fourier transform of psi, which is phi, and the Fourier transform 1/r, which I write like that. But the next line will write down the Fourier transform of this one because we have done that before, right? 1/r, the Fourier transform 1/r, we have done that before. So yeah, okay, I'm going to look at it. Right. E is a constant in quantum mechanics. E is a constant. It's eigenvalue of the you can say the Hamiltonian operator. One over r is not in the original equation. One over r is just the potential. It's just the distance between the origin. This is the Fourier transform of psi. This is phi is the Fourier transform of psi, and this notation is the Fourier transform of 1 over r. R is in 3 dimensions. R is x squared plus y squared plus z squared. It's the radial distance. So you have a this is like a charge inside at the origin, and then distance r in 3 dimension space. Okay. This one? This one?
It should be in 3D.
Yeah, it doesn't matter.
Yeah, it's everything in 3D. Yeah, this is example in 3 dimensions. Okay. Yeah. All right. Now the rest is just look up this one of all, which we did that in the discussion of 3D transform. That's equation 2142 by 2142. So just write like copy this term, and this is 1 over 2 pi 3/2 and multiplied by 4 pi divided by k squared. So altogether you have 2 pi cubic power, and then another 4 pi factor in front. And then it's k. And 1 over k squared becomes this k minus k pi squared. Okay, and then dq. Oh, this is pi. Dq pi. All right. So this equals to that. This equals to that. It equals to this one. It's the same. Okay. Now this is still a difficult equation to solve. This is the integral equation. Now it's not a differential equation. It's a different integral equation for this phi function. So generally how to solve it is beyond us. But what this example your textbook is saying that just check a function that you already can see how it satisfies this equation if psi is proportional to this e to the minus. You can check that this is a distribution of this one, and so obviously you substitute this, you check that it's a solution, and then you can solve for e, and that's trivial. I mean, not trivial, but straightforward. But now you can also check that the Fourier transform of this one satisfies this equation, and that is also not trivial. But the Fourier transform of this exponential function we also have done with psi k is any constant. These are linear equations, so you can always multiply any constant. And sometimes you want to normalize that also. But without consider normalization, just keep a constant. And then the Fourier transform of e to the minus r. Again, this is a 3D transform. We did that in this is the last equation, right? This is e to the minus r. minus e
minus the,
e to the minus 1. Right, so it's 20.44. This is 20.44. So that equation is e to minus z are also, so you need to set c equals 1. So that is 8 pi divided by 2 pi 3/2 k squared c is 1 squared plus 1 squared. Okay, and that is and then actually your text will absorb all these in the constants, so we define it as c. It doesn't matter. Again, it's a linear function, a linear equation. Okay, so you just substitute this into here, and then check whether that is satisfied, and then solve for e, and which is doable. So the only difficulty, or slight difficulty, is this: you need the integral of this form, or of this form. So you already have this one, so you need to do an integration in 3D, something like you have a dq k, right? And then respective k minus k pi. Yeah, there's one question. And you need to do this integral. Square, this is square, this is square. Right? Which is doable. Again, that's straightforward, but I don't have time to do it. I did it in again another video YouTube channel. If you like how to solve it, you can do it. I think you can do it in elementary method with the complex integral. But what I did is using complex integral first to evaluate, simplify this, doing some angular integration first, and finally is reduce it to just one complex integral, which is straightforward. So you have two residues to sum. That's straightforward. But after you do that and substitute that back to the equation, and then you can solve for e. And, what the solution is e equals to minus 1/2. Okay. It can be done, but just without doing it, that you need to just trust the textbook. Okay. Okay, that's the last example. So that's this section conclusion. Any question? Last minute question before we move on. We C is just a constant. It doesn't matter because this is I already said that this is all these are linear equations. Linear means you multiply another constant in front of your solution, doesn't change your solution. It's any number is fine. So if later on you can fix that by normalization. Usually we require that. Now you go back to the physical space, the psi square, dqx is equals to 1. You can normalize that, right? And by the Parseval theorem, this is also using our symmetric notation. This is also the same. You can normalize that. So once you solve a final solution, if you like to fix this constant, you just normalize it. Is that okay?
Yeah.
You talk about this constant, right? It doesn't matter. It can be any number. Once it normalized, it doesn't matter. When it's normalized, you can fix this. And you fix it up to a phase. right? Because this is absolute value. So we can multiply a phase also. Multiply C as a complex number, we see the phase doesn't matter. You can. This is quantum mechanics. Right? It can be real or complex. You multiply a phase doesn't change anything.
I see.
Yeah, C. You can multiply by phase. You're just looking for eigenfunction. So this equation is look for an eigenfunction for a eigenvalue E, and you fix the eigenfunction up to a phase. Actually, after normalization, you still have a phase. Okay, eigenvalue is arbitrary up to a phase. So it's okay. So you don't. But for our purpose, if you just want the eigenvalue, then it doesn't matter. You still get exactly the same eigenvalue, whatever the C value is, because this is linear function. This is linear equation. Okay. And sometimes we don't concern. I mean, after you want to calculate other things, you maybe a probability of finding a certain particle over a certain region, then you need to normalize that because now you interpret that as a probability because the total probability is 1. Right? So you just make that interpretation.